It is really a pleasure this afternoon to welcome our guest and friend, Marina Rejkuba from ESO. I mean, for many of us, Marina doesn't need any presentation, but let me introduce her to the wider community present here. So Marina is an ESO associate astronomer. She got her PhD at PUC in Chile in 2002 with a thesis on resolved stellar populations. And after she moved in Gatching as an ESO fellow from 2002 to 2005, and afterwards she started as a position as a faculty astronomer at ESO. Since 2015, Marina is head of the user support department again at ESO. She has a very long CV. I cannot go through all of it, but now I'm speaking English, but Marina is also very fluent in Italian because she also has been, she's Croatian, but she's also been undergraduate student and then research assistant in Italy for a few years. Her research interests cover from observational astronomy, optical and near-infrared photometry and spectroscopy, and then to many science. She has a lot of science interests covering galaxy halos, formation and evolution of galaxies, stellar populations, variable stars, globular clusters, and globular cluster systems. The distance scale, so a lot. There's a lot of science. But today, Marina will have, her talk will be very much focused on something related to stellar populations, and she will, the title of her presentation is Unraveling the Formation History of the Nearest Giant Elliptical Galaxy. A few information for all of us. Marina, I leave you the microphone. I will inform you 5 minutes ahead of time. For the other participants, please mute your microphone. We also have a streaming. For those participating through the stream, you can write your questions there, and at the end of the seminar, we will read the questions. So again, Marina, thank you, and the microphone is yours.
Thank you, thanks, Mick. It's really a pleasure, and I'm looking forward to sharing with you some of the work that has been accumulating over many, many years. As a matter of fact, the galaxy that I will be talking about in this seminar, Centaurus A, has been the galaxy that has kept my interest since my PhD. And during my PhD, when I met also Laura Greggio, Bill Harris, with whom I kept on collaborating over the years as we explore and learn more about this galaxy. In this talk, I will be presenting some of the recent results, but I will give you a little bit also an overview of how we came there, what was also what we have done in the past. So it's really not only one paper, but it's really going through a lot of things. But just to introduce the topic first, I will start very general. We know that the galaxies form in a hierarchical manner. The model of the formation of galaxies tells us that we start with first stars, protogalaxies, that galaxies accumulate gas through the filaments, keep on growing, and then that their morphological transformation happens mostly through mergers, major minor mergers, accretions, and eventually over time we build up to have the large spheroids. And nowadays the cosmological simulations are really becoming very powerful. In this paper by Mancillas et al., they have simulated individual galaxies that can be very nicely compared to the observations that are here on the left side that come from the MAPPA survey from Pierre Landuc and collaborators. And the simulations look pretty much alike, producing a plethora of low surface brightness features that one can see around these galaxies. So nowadays the technology and observational capabilities have increased so much that we can really start tracing assembly history around individual galaxies through these streams, tidal tails, shells. Comparing these observations and the simulations then leads to conclusions about how fast these mergers happen, how many of the faint substructures one can expect to see, and how long they last. As a matter of fact, most of these faint substructures that are visible here and this scale of the order of 29 magnitude per square second surface brightness, they are tracing really the largest and most recent accretion events, and they survive up to about several gigayears. This accretion and assembly of galaxies is particularly well explored in nearby clusters, where we can see lots of light that is connecting galaxies, and that really shows how the galaxies are changing as they are in these very dense environments. There is wonderful work by Chris Michos and also in Erika Jodic and Rilena Spalvone, Vega's team, leading the exploration of the faint outskirts of galaxies in different environments that shows how these galaxies there transform and what we can learn about their formation from these integrated light studies. Another example that I already mentioned is the MATLAS survey, and more is certainly coming with LSST, with Euclid. So when we look at this assembly as a function of surface brightness, I really like to look at this series of images that have been made already 15 years ago by Johnson and Bullock, where they looked at the Milky Way type galaxy, and they highlighted the particles that one would see depending on how deep the observations could be. At 40 magnitudes per square second, something that is totally non-achievable observationally, this is why I say theory is ahead of observations here. This is what they predict that we would be seeing. And as we go to brighter and brighter surface brightness limits, certain features that we were seeing before are simply starting to disappear. And as we go to even brighter, they become less and less. And this is where really the limits of the integrated light studies come in. So first of all, they are seeing only the most recent, most massive events in the halos of the galaxies. They have observationally, they are really difficult observations because they really require exquisite flat fielding and sky subtraction techniques, and the scattered light and cirrus are nuisance that needs to be dealt with. On the side of the advantages, certainly very important one is that nowadays we have wide field cameras and panoramic views of galaxies are possible. We can get very efficiently census of substructures around the galaxies, and then we can get stellar surface density profiles, full range of galaxy masses in different environments, and larger samples for stacking or for average properties of these galaxies. And of course, we always get, as a bonus, globular cluster systems. And if certain filters, observing techniques are used, we can get also planetary nebula. In terms of stellar population analysis, there is always a limitation of the H-metallicity degeneracy with the optical probe filters, of course, which can be broken if one combines multiple filters and adds some spectroscopy or spectral fitting, which then, however, is limited to the more nearby and brighter objects. As an example of these difficult imaging techniques, I bring back my favorite galaxy, NGC 5128 Centaurus A, and this is how it looks like with a very deep exposure from David Malin, where one can see a huge amount of substructures around it, but actually most of this stuff is just galactic cirrus. It's not belonging to the galaxy, but is something that is in between us, which makes this galaxy particularly not suitable for integrated light, wide field studies. And instead, the resolved stellar population comes to the rescue in this case. In that case, we are caring a little bit less about flat fielding and sky subtraction because we are looking at things locally, so we can subtract that and model that locally much easier. And we can have unambiguous detection of individual stars that can give us then also the distances, surface density gradients, and also the metallicity distribution in individual fields. So we can start studying how, not only what is the average metallicity at different distances, but maybe also how the metallicity distribution changes or doesn't change as we go further out. It also allows us to go to much fainter surface density, surface brightness limits. In some cases, up to about 34 magnitudes per square arc second. As I'll show in a moment, this depends really on the depth of the observations themselves. And this then can allow to trace smaller accretion events or older ones. Globular clusters, planetary nebula are coming in there in the same way as for integrated light. And then we can also get some handle on the age and star formation history. Of course, one of the big limitations is this is limited to nearby systems. From the ground, 5 to 10 megaparsec. HST opened the space to about 20 megaparsec, but really at the very brightest edge. JWST pushes this limit a little bit further, but the time there is very limited, so we'll see how much will come in with time. And certainly this will remain as limited to relatively small samples that will grow only slowly. Nevertheless, it is important as a cross-check and a complementary way of studying the nearby galaxies. One other limitation that I need to mention here is the foreground stars and background galaxies that can contaminate our samples and need to be taken care of. Gaia for the Milky Way has completely revolutionized this field. So here we have from individual stars, we can get their kinematics, their radial velocities, their transversal velocities, and really completely resolve the halo of the Milky Way into individual streams, and then look for progenitors that build up the Milky Way. This is something that will remain also in the future limited to the Milky Way. For the nearby galaxies, we can dream of going to the surveys such as PANDAS, where we can see resolved stars, so individual stars, and they're color-coded here according to their metallicity. And we can see how the halo of M31 here imaged out to 150 kiloparsec looks like, how their different streams over densities, shells, and from their combining all of these, comparing them eventually to the simulations, one can better understand how these galaxies form. So how do we do that? We do that through photometry. I will be speaking mostly here, entirely here about the optical photometry. And in large majority of the cases, we have used optical V and I band filters, because this is where most of the stars have got their surface spectral energy distribution, and therefore they are brightest, they are easiest to observe there. Here in this simulated color magnitude diagram, we can see stars color-coded according to their age, and we can see how the turn-off region of the main sequence is really the most sensitive indicator of the age of the stars. As they evolve, they climb along the red giant branch, and here there is relatively little information about the age of the stars, and where the red giant branch stars start to be interesting for metallicity distribution measurements. red clump and horizontal branch are again very strong age indicators. So how far can we use these color magnitude diagrams of nearby galaxies to reconstruct their star formation histories, to reconstruct their metallicity distributions, their density distributions? Here I have put some lines. This is really very, very rough, but we can resolve the main sequence turnoffs for all the galaxies in the local group, all the way to the edge of the local group, nowadays with ground-based deep observations or space telescope observations. With deepest observations with the HST, we have reached core helium burning red clump stars in Cen A, and I will show some of these results from that study. But we are beyond the local group. We are essentially observing the red giant branch. With JWST, we can go in the very outskirts. We can go a little bit deeper, but we are still very much limited by the resolution to core helium burning and red giant branch. So this study that we are doing now for Cen A is state of the art until we can reach much deeper and image with ELP the turnoff for the brighter younger populations, if there are any. Another trade-off that one needs to certainly think about is the depth versus area. Here I'm showing a luminosity function for a single stellar population where we have the isochrones, star evolutionary models for different ages, for 1, 3, and 10 giga-years, and for two different metallicity of about LMC or a little bit more around the metallicity of the LMC and a somewhat more metal poor one. And essentially, if we are able to observe stars, so here at -4 is where we can see that the luminosity function really drops off for the old populations, because this is where we have a tip of the red giant branch. So there are no more stars brighter than about -4. And if we just then integrate how many stars are we going to see if we are able to observe to about -2 magnitude in I band, depending on the age of the population, we are going to see a different number of stars. So we can use this diagnostic also to probe how far in the surface brightness we will be able to reach, and what will be the possibility to distinguish the populations. So what did we do for Centaurus A NGC 5128? First of all, why did we choose it? This is the first, Centaurus A NGC 5128 is a galaxy in the center of the nearby group at 4 megaparsec, 3.8. And it is the nearest easily observable elliptical galaxy. A lot of people initially, when we were putting in proposals, were saying, but what you're going to learn about it, this is a recent merger, it's not a typical elliptical galaxy. But then came other studies that showed that in the nearby universe, a lot of galaxies, really of the order of 60%, have features in their light distribution that indicate recent interactions, recent mergers. Cen A is furthermore a radio galaxy. It has a central supermassive black hole, which is something that is really typical for massive galaxies. And there was a paper written some years ago by Gretchen Harris that really argued how Cen A is a normal elliptical, typical representative of its class. As usual, when we start looking things into detail, we find peculiarities, and this is where the interest really comes. We keep on digging further. So here is an image of Cen A, where we can see this central region that has this dust lane. There are some bright supergiant stars along the dust lane, so there is some star formation. There is quite a lot of dust and gas in the central region. which is why this is thought of being a remnant of a recent merger. Now, a deep optical image processed with unsharp masking showed a much wider distribution of shells around this galaxy. This is from Eric Peng in 2002, and if I flip back, you can see really how this goes all the way to about 15 kiloparsec out in the halo, extending with lots of these features. But beyond that, halo really, from the ground, at least from the imaging that we have, looks fairly smooth and looks unperturbed. So how does the light distribution, what kind of stars do we have in the halo really far away from this central perturbed region? So this is where we initially started investigating these outlying halo fields where we just stare at nothing and try to find out how far the galaxy really extends, how far away does it go. So these two fields, I'm just going to mark them as, just for example, to show in perspective how far we are going. These are two ACS pointings that are along the minor axis, and these two ACS pointings are this one and this one here. So these are along the minor axis. This black square is the size of this image that showed all these shells and substructures. Now, the HST observations of Cen A started shortly after the HST was launched, and then the camera was refurbished, etc. So there were a slow build-up of the fields. So the numbering of the fields really reflects more how they were acquired throughout the years with different observing proposals than really a very sensible numbering. But that's what life is. So here I'm going to talk much more. So we have observations that span here of the order of 140 kiloparsec along the major and 90 kiloparsec along the minor axis. I'll show later there are further additional fields that we have added to this collection. And I will first concentrate on this field that is here in the south, called F4 for us, which is the deepest field in which we have reached core helium burning stars. So this is the column magnitude diagram of this field, which was one of the first observations with the ACS camera in the beginning of 2000, 2002, 2003. And we have 24 orbits with 12 orbits with V band and 12 orbits in I band, and we can really nicely see here the red clump in this galaxy. This is simply the same, just showed the two different scalings. I think here one can see this overdensity both for the red clump and for the AGB bump, while here maybe the morphology of that clump comes in a little bit nicer. Now, one of the first things one can see here, there is all this stuff above, and this is foreground. When we take either a foreground background field that is further away from this, of course, we have to go very far away in order not to hit another field in the halo of the galaxy. So this is the tricky part. Or we can take the Milky Way simulation from Besançon, from Trilegal, to subtract the expected Milky Way foreground. So all of these stars up here are the foreground stars. And after subtracting those, we are left with the column magnitude diagram that belongs to the galaxy itself, where we see this very sharp edge, which is the tip of the red giant branch, and we can use it to measure the distance to the galaxy. This was one of the ways of measuring the distance. One can also use the red clump to measure the distance, but the red clump starts to be age sensitive as well. So we need to first make sure that we are using the right magnitude there. Okay, so going back to this column magnitude diagram, what do we see? We see the red giant branch here. In the upper part, we see the AGB bump red clump. And overplotted here are the isochrones. These are older, past the isochrones. I think that had also the extension towards to the AGB population. And here we can see that just simply looking at the spread of the red giant branch stars in this column magnitude diagram and taking a 13 giga-year-old solar scale metallicity isochrone, it's this solid line, and 3 giga-year-old solar scale, you can see how little the red giant branch is responsive to the age. So between 3 and 13 giga-year-old, for the same metallicity, we don't move almost anything in color. A little bit more on the metal rich end. On the metal rich end here, we have the solar scale and the 13 giga-year-old solar scale. Instead, there is a very high sensitivity to metallicity. However, we cannot get the full color range that we see in the stars by saying, okay, the metal poor stars are old, and then progressively we having reached the abundances, the enrichment went on as the new stars were formed, and the metal rich stars are younger. This is simply not possible to achieve here, because we can see that even with solar metallicity 3 giga-year-old population, we are nowhere near the red edge of the red giant branch that is observed here. So we already simply by observing this, comparing the isochrones with the observed column magnitude diagram, we can say that we need to have some very high metallicity stars in there, and we need to have some old ages in there. The other features, AGB bump, the red clump, can be further used to constrain the age range in this field. And this can be done by comparing the observed column magnitude diagram with simulations. And in this case, I have a set of sample observations, sample simulations here, just to highlight the sensitivity of the red clump magnitude. In each case in this diagram, the line is always at the same magnitude, just to show how in a 6 giga-year-old population, the red clump is significantly brighter than it gets as we go to the older and older populations. So comparing the distribution of stars in the red clump along the red giant branch with the observation gives us a possibility to constrain the age distribution of the stars in the halo. This is what we did in some 10 years ago with this field, and we have concluded that the bulk of the stars there are old. They are best fitted with two bursts. Single stellar population, just purely old, doesn't work. It's producing a poor match to the observations. But if we mix about 20 to 30% in mass of the younger population, we are reaching a good fit between the observed column magnitude diagram and the simulation. Now, in the meantime, many additional fields have been observed. These are all these brown colored, mustard colored fields that have been taken as parallel observations with BPIC-3 camera, where the primary observing goal of that program was actually to observe dwarf galaxy candidates that were detected in the halo, behind the halo of Cen A. Some of these dwarfs were confirmed, some of them turned out to be simply stars in the halo. But we have taken advantage of these parallel observations as well to have many more probes of the halo and properties of the halo stars. So this is just a panorama of all the column magnitude diagrams, where we can see the column magnitude diagrams that were taken. So here, just as a note before, we had these dark gray fields that were designed to probe the halo of Cen A, and they had deeper exposure. So these fields had one orbit in B and one orbit in I band, so they reach a little bit deeper than these parallel observations that were focusing on confirming the dwarf galaxies. But still, we can see that the color magnitude diagrams for the fields that have that are closer in towards the center of the galaxy are still fairly well populated, and we can recognize the red giant branch in all of them. And then we have some of the outermost fields that start to be just a bunch of stars that are hardly resembling any coherent structure of the red giant branch. So how do we deal with these observations? One of the first things we need to consider is this foreground contamination. Do we actually see still any trace of the halo in these fields that are far out, or do we see only the foreground? So for that, we have scoured the whole archive, HST archive, and tried to find all the observations that could be suitable for foreground background decontamination. And we have also experimented with simulated Milky Way simulated fields in the direction of the Cen A using trilegal and also Besançon simulations. Here on the left, we can see what we expect the foreground to look like according to trilegal simulation, where we have simulated the area that corresponds to combined 5 ACS plus 5 VPIC-3 observations. So it's much larger area than one single field. And this is where the stars will be distributed. So this is where we can expect also in the observed fields that the stars are distributed. And as a matter of fact, this background field that we have found in the archive seems to have mostly these stars that are expected to be there from the Milky Way. It has also some of these additional stars in the bluer part that could be background galaxies, could be artifacts from the photometry. It's all together. So this is where we experimented with different types of foreground contamination. In the end, ended up using this background field to decontaminate point by point our color magnitude diagrams. And here we can see an example one for one of the fields where how it looks like after decontamination. It's not perfect. There are still some traces up there, but most of the stars that belong to the foreground background are gone. So then we start exploring these fields, and this is where we notice that in almost all of the fields that are within the about 30, 40 kiloparsec distance from the center of the Cen A, if we just look at the number of stars, so this diagram has a number of stars per square arc minute. In each point is a different field, and these fields are arranged according to their projected distance from the center of the galaxy. And we have seen that there is a tip of the red giant branch after correction for the extinction, etc., is at 23.86. So this is now above the tip of the red giant branch. We are seeing stars. Even one magnitude above, we still see some slight, perhaps, excess. So what are these stars? We first started to look whether this could be still remnants from the decontamination from the foreground background stars. This is definitely not the case because these color magnitude diagrams have been already decontaminated, so they have been, all the foreground background has been removed, and this is after removal comparing to the entire field that has this foreground star, so we have definitely many more. Another question was whether this could be blends, but we really inspected very carefully the images, added artificial stars, recovered them, did all the completeness analysis. It really simply didn't work. So one of the possibilities could be, hey, maybe we are seeing some structures in between us and the Cen A. Maybe there are some, unseen, very faint, very diffuse dwarf galaxies in between. But again, that didn't work because simply these fields are very far apart from each other. The W6 with respect to this W10, 11, it's completely on the other side of the galaxy, so it simply cannot fit there. And so this is where we ended up thinking, okay, this could be an intermediate age population. But one puzzling thing was how come this falls off and comes down? So this is where we also started investigating overall distribution of stars in Cen A and looking at the stellar density profiles. So earlier when I showed you the distribution of fields on the galaxy, there were all these elliptical annuli, and these ellipses are simply the same elliptical annulus just extending further out from the profile that was measured on photographic plates by Dufour et al. In 1979. And they have measured the axis ratio of 0.77 in the inner one effective radius or so, a little bit more. And if we then extend this ellipticity, I mean, you assume that the profile is exactly the same all across the entire galaxy, and we count the number of stars as a function of distance, fit it with the power law. This is what we get. And we can see that there is quite some residual that seems to have some systematics. So this is where we started varying the axis ratio for the further out as we go. And we found that we can minimize the scatter if we have the axis ratio of 0.54. So the ellipticity increases further out. With this outer halo ellipticity or axis ratio, we can best fit the whole profile of the entire galaxy from the inner parts, from the photographic profile from photographic plates, and then we splice to it our star counts. And this is where we can see that we are tracing very nicely the halo out to about 32 magnitudes per square second. Now, assuming that, taking now into account that our ellipticity in the outer fields increases, all our fields start to rearrange themselves. The distances, the projected distances change. So if we project the distance to each field from where it was before projected on its elliptical annulus to the new 0.54, we can see that W7, for example, which was very close in, now jumps further out, while some of the other fields that were along the major axis remain roughly the same distances. So rearranging all these fields suddenly led us to very nice, smooth decrease in this excess of stars as we go further out. And that indicated, okay, here we have some additional component in the stellar population. So is this additional component explainable? How can you explain it with AGB component, younger age? So here are the stellar evolutionary tracks. In red, we have red giant branch stars. Blue is early AGB, and the red is the TP-AGB. These are the models from Padova, from Parsec with Colibri extension of the TP-AGB. And here, if we count the number of stars in the box here in the column diagram, which is the red giant branch box, and compare it with the number of stars in the AGB box, which is above the tip of the red giant branch, we can make this ratio of the number of AGB, number of red giant branch stars. We can compare it in the same way also for the isochrones for different ages, and then we can construct these ratios of the number of AGB, number of red giant branch stars as a function of fraction of old plus young population. So in these different lines, we have 10 giga-year-old population plus a 2 giga-year-old younger population that contributes about 5%, 20%, 40%, etc. So this is how the ratio of these AGB, RGB stars would be. And then we have this dashed band, which tells us how many stars, what is the ratio of the AGB over RGB stars that we observe in these fields that are over there. And this can be explained either with about less than 10% of the very young 2 giga-year-old population, or with about 30% of slightly older population. If we then add also the excess of stars above, in the box above here, then we really need this very young population. So essentially, with this, we are putting a limit on the total fraction in mass of the young population, independently from these bright stars that is in the order of 2 to 3 giga-years and a fraction of about between 10 to 30%. Again, confirming the result that we had before from the full fitting of the very deep color-magnitude diagram. So this intermediate age component was already suspected before. This was my PhD thesis work, actually, where I had multi-epoch photometry of Cen A fields with Isaac, with the near infrared, and all these red circle stars above the tip of the red giant branch turned out to be variables. And these variables are Mira variables with their periods consistent with about a small fraction of them being also intermediate age AGB stars because of their very long periods. However, the metallicity period age degeneracy for the LPEs was at that time a bit limiting what we could do at that, how precisely we could determine this intermediate age component. Another line of evidence for this intermediate age component comes also from the study of globular clusters, and this is from a PhD thesis of Kirsten Woodley, who has looked at who had spectroscopy of quite a large sample of globular clusters in Cen A, and who determined this multimodal distribution of ages of globular clusters in Cen A, which is much more extended than what we can see in the Milky Way. Similar conclusion was reached by Beasley et al. Again, globular clusters in Cen A are the black dots. Milky Way comparison are from Schiavone and Puzzi et al. Are in open symbols here. Okay, so besides, once we know the ages, we need to go to the metallicity distributions. The way we are determining the metallicity distributions for all these fields is that we take the stellar evolutionary models from Basti, and we are simulating color magnitude diagrams with some single age, where we assume an old age because we don't really know which star has which age. We know that we have a little bit of some contribution of the intermediate age, but at the moment we are ignoring that. And then we take the simulation and compare it to the observations and really match simulated star to the observed star and assign to the observed star the metallicity of the simulated star. And this is how we can color code the observed color magnitude diagram with colors that correspond to the metallicity of the simulation. Expressed in a metallicity distribution, this is for our best field at 4, the metallicity distribution that we are getting from the stars that are above 26 magnitude. For all other fields, we need to limit to slightly brighter magnitudes because of the larger errors. So this histogram actually limits to 25.6 magnitudes. And here we can run Gaussian mixture modeling in order to determine how many components do we really have in the halo. And in this case, we are getting the best fit with 2 components, with one peaking at close to slightly below solar, and the other one at around -1. So this field is already some 40 kiloparsec out in the halo. Already at this large distance, we have really high metallicity, a lot of stars with very high metallicity. Then we can look at how the metallicity distributions change from field to field. Here are the metallicity distributions for all the fields that are here in this distributed across the face of the galaxy, and they're ordered in their distance, projected to the distance along the ellipse along the semi-major axis. So essentially, if I have this field here, its distance is the same as here. So that means that this field, that's whatever, W2 is really one of the most distant fields and contributes to the most distant field. So what we can see is that, so these are smoothed histograms, these are kernel KD distributions of the histograms of the metallicity distributions for individual fields. What we can see is that the peak at the high metallicity persists very far out to 11, essentially to 11 effective radius. One effective radius is 5.6 kiloparsec. So here we are at about 60 kiloparsecs out in the halo. There is this metal-rich peak, however, decreases steadily as we go further out and gets less intensive, less populated with respect to the metal poor one. The change really happens around 15, 16 effective radii, so at about 90 kiloparsec, so that's around here. For the last two bins, I have not made distributions for individual fields because simply we have such a scatter of stars that is really not really sensible to make individual distributions, but I have just bunched them together and we don't see really a very big change beyond this limit here. There is still quite a substantial number of relatively metal-rich stars, and to be honest, I'm still puzzled by that. That's something that we are still trying to understand, how much this is due to the limitation in our photometry, how much this is really real. But we can start looking at the metallicity gradients, and here is just plotting median metallicity for each of these fields and fitting a line without justifying that this is a line. And we can see a relatively shallow metallicity gradient that goes down, and then in these very outermost fields, I think here, this really, the individual fields doesn't make much sense to look at this median metallicity, so that's something to be checked. How much residual contamination from the foreground affects the shifts in the metallicity. But we can start also looking at how the blue and the red peak changes. What we are seeing essentially that it doesn't change at all until about 100 kiloparsec, and then it starts to drop. So that's something where we can start seeing in the very outer edges of the halos, the smaller satellites accreting, contributing more to the halo, while the inner parts are still fairly metal-rich. So these are
we have 5 minutes.
Okay, that's perfect. So these are the conclusions from this observational part. Essentially what we are seeing is that the halo extends really far out beyond about 140 kiloparsec. If you just go along the major axis projecting, if we are taking also this elliptical annuli, we can even extend it further, but okay, that depends how well we can measure this flattening of the halo with the number of fields we have. We see fairly high median metallicity, and this surface brightness is traced down to very faint magnitudes. Now, this, of course, we see quite a lot of scatter. I mean, I have shown you before, this was just fit with the line, but you can see that individual fields scatter all around the line. And particularly egregious example is this one at F6, where we have two fields that are very close to nearby, and they differ in median metallicity by half a dex. And this is because we are hitting substructures. And as a matter of fact, close inspection of the panoramic image of Cen A done by Daniel Martinovic at Magellan, with Megacam and Magellan, turned out that our field 6 was just on top of this stream. So here we were actually measuring metallicity of this stream, of this disrupted core. And this is where we really need to combine this wide area imaging that will come from Euclid, from LSST, where we do not have the possibility to really measure precisely the regenerate stars individually here because they're overwhelmed by too high contamination from foreground, background because of the limited resolution of the images. And that we can get all these substructures and interpret better our deep observations. Now, in the last minute, I'm just going to flash one of the possible explanations for it. So this image has actually triggered, this stream has triggered a discussion about formation of Cen A. So one of the possibilities that was put forward by François Hammer, who was very eager to demonstrate ability to reproduce all of these features with a single major merger, triggered comparison of their simulations with the single major merger with all the observational data sets. And this is what is shown here. So here we have a major merger that starts about 5 gigayears ago with two disks that are coming together, backsplashing around, producing a lot of shells, and also producing, if I manage to stop this, and also producing this straight stream that resembles very much this stream that could alternatively very well be explained also by a stripped dwarf galaxy. So we have then used these simulations that state that Cen A would have formed from a major merger some 5 gigayears ago and tried to look at which of the observables we could reproduce. We could roughly reproduce the morphology and the faint features. There are all these shells, and the inner shells is very well reproduced. The scale is not reproduced. The total mass distribution is reproduced, and the stellar mass profile. Metallicity distribution I'll show, and amount of dust and star formation in the central parts, of course, varying the amount of gas in these two these galaxies that are coming together. So this is how these different merger models look like and how they compare morphologically with these faint features out there. And the predictions from this model also comes to prediction for the relative distance of the stream with respect to the halo, where it will be in front or behind. And so this is something that can be tested observationally. Other comparison that we did was with kinematics of planetary nebula and globular clusters. And here is the final one with metallicity distribution, which we had at that time from the fewer fields. But the red is the model, and the black and green are the observed metallicity distribution. And here the distribution at different distances, how well they can match. So with this, I think I will stop, share my summary slide, and